So we talk about 14.2, which is algebra, or really the algebraic techniques for finding a limit of a function. Really just a continuation of 14.1, where 14.1 was looking at the graph, looking at the tables of certain functions to figure out how the functions behave near a certain number. But we throw in a little bit of an algebra twist into 14.2, but it's really all the same stuff. We have one learning target for today. I can find the limit of a sum, difference, product, polynomial, power of a root, and quotient. I want to make a little list over here of the different types of functions that you may see. And the first one that we will talk about is the constant function, where the function is just a number or really just a horizontal line. So I want to find the limit because, once again, to find the limit of a function is abbreviated LIM, of a number as x approaches c of b. Now remember, b is my function, right? And so if we kind of just think about a quick graph of what this looks like, if b is a function where b is just a number like 4 or 6 or 9, it's just going to be a horizontal line, right? C is the x value. So if you think about the x value right over here as c, this value, right, how high is this up off the graph? If I come in from the right or from the positive side, if I come in from the left or from the negative side, those numbers are both approaching the same value, and that value is b. Because say this number is 4, this is a horizontal line through 4. So this is just equal to b. The next one is called the identity function, which you know very well. So again, I want to find the limit as x approaches c of x. Let's see what this is going to be from a graphical standpoint. Well, x is y equals x, which is my function which has a slope of 1, which is a linear function which looks something like this. X is my c value. And like, say if this is the value c, what is this number? Right? So we want to look at what the value is. If I come in from the right, from the positive side, it approaches this number, this y value. If I come in from the left, from the negative side, it approaches the same number, so I know that it's defined. And this number is actually c, right? Because the point 4, 4 or 12, 12 or 90, 90 is a point that's on my function y equals x. I want to give you another list of the rest of the types that you're going to see. The first three, which are going to be sum, difference, and product, are going to look exactly the same. I'm going to say that this is the limit as x approaches c, and we're going to write this as two separate functions. Let's call them f of x and g of x. This is really going to be intuitive, and I'll show you why this is going to be true here in just a second. I can take the limit and I can apply it to each function. Is the limit as x approaches c of my first function added to the limit as x approaches c of my second function. So you can split them up like this, right? And now the difference is the same exact thing, except I can just have a minus and I can subtract the 2. The product is just the same exact thing. I can take the quantity of two functions multiplied together and take the limit. Is the same exact thing as taking the limit of the two separate functions and then multiplying the results together. My next type is of a polynomial. We'll look at the examples here in just a minute. But if I'm going to take the limit as x approaches c, let's call the polynomial p, or p of x, is really just my polynomial evaluated at c. Because if I take the x value at c, can I just plug that number into the function and get the y value? Because if you remember from up here, the y value is the limit of the function, right? If I take the limit of x, which is this linear line, this linear function right here, is going to be the evaluation, right, or the y value of that function. And if I take the limit that I have, say as x approaches 5, and I can take 5 and plug it in, that would give me the y value of my polynomial evaluated at 5. The same is true as power and root. I can take the limit as x approaches c of a function raised to the nth power. This is identical to the limit as x approaches c of my function, and that limit raised to the nth power. Now, this power could be the second power, like a squared, or the fourth power, or the ninth power. It could also be a 1/2 power. And if this is a 1/2 power, I can take the square root I could take the square root function, evaluate the limit. It is the same as the limit of the function and the square root of that number. So I could have a power and a root. Those are going to give you the same solution. And finally, for my last type, my last general type, is a quotient. It's exactly like the sum difference and product. So let's look at a couple of examples. A lot of them will go very quickly, and then we can make some sense out of all this business. The first one is I want to find the limit as x approaches 4 of 12. So let's think about this for a minute. 12 is just a constant. It's a constant function. It's a horizontal line through 12. And if I find my x value, just kind of think of a little graph right here. Here's a horizontal line through 12. My x value is 4. I go over to 4, and that number is going to be 12 because the y value is going to be 12. So the answer here is going to be 12. And that is all. Example 2, I could find the limit of x as x approaches negative 7. And once again, think about what this is. This is a linear function with a slope of 1. And the point negative 7 is on my function, right? Think about the graph of it. I'll draw it up here. There's y equals x. Okay, I could go over to negative 7, which is to the left, and then down to negative 7. That's the point on my graph. So my answer here is going to be negative 7. Just remember, if I have a constant, the solution is the constant. And if I have the identity function, the solution is the x value that you are approaching. Similarly, I could have something like number 3, the limit as x approaches 8 of x plus 9. Now think of this in two ways very quickly. My sum general formula says I could have two functions, f plus g, and then I can separate them. So really I have two functions, which is x plus 9. And so I could rewrite this as the limit as x approaches 8 of x plus the limit as x approaches 8 of 9. And what did we just learn in the last two examples? Well, the limit as x approaches 8 of the identity function x is really just that number. Let's call that 8. And the limit of a constant function 9 is the y value of that constant, which is just going to be 9. So my final answer here is going to be 17. Now, do we need to do this? We don't need to separate these. The rule just tells you that you can. All that I need to do is take the 8 and plug it into my function. Because remember, the general form says that in a polynomial, I can take the x value and plug it into that polynomial to get the limit. So I could take the x value, 8, and I could plug that into my function to get the limit. And once again, 8 plus 9 is 17. And so that's how we can get that. Similarly, we look at something like this, number 4. The limit as x approaches negative 2 of the polynomial 3x cubed, right? Do I need to break all this up using the quotient formula and using the power and root formulas, the general forms? You don't have to do that. If I write this as a polynomial, I can take my negative 2 and I can just plug it in. So the limit is just going to be 3 evaluated at negative 2 to the third power. Well, I know my exponent goes first, so this is going to be 3. Negative 2 to the third power is negative 2 times negative 2 times negative 2, which is negative 8. So the limit of this function is negative 24. 3 more examples here. Let's jump over here to number 5. I want to find the limit as x approaches 1 of 5x minus 2 over x squared plus 6x plus 2, right? So this is, again, a polynomial over a polynomial, or really a quotient formula that we have listed up here, right? So a function over a function. I can find the limit of each one, and then I can just divide the two. Well, isn't each one of these individually just a polynomial? Since this is just a polynomial, I can just take 1 and plug it in. And so 1 plugged into the top is 5 minus 2, which is 3. 1 plugged into the bottom is 1 squared, which is 1, plus 6 times 1, which is 6, plus 2. 1 plus 6 is 7, plus 2 is 9. So my final answer is 3/9, which I always need to reduce to 1/3. Let's find the limit as x approaches 4 of x squared plus 3x minus 28. Now, all those properties that I showed you before are always true. Now, the problem here is that since I even still have a polynomial over a polynomial, or the quotient rule, I could take my c value, or the value that my limit is approaching, and plug it in. However, that gives me 0 in the bottom. what would that be? 16 plus 12 is 28 minus 28. Well, that's going to be 0 over 0. And really anything with 0 on the bottom is undefined. This is very strange. So now the algebra techniques come in. In this case, I could take the top and I could factor it. So let's try to factor it using reverse FOIL. X squared is going to be x times x. What are the factors of 28 that subtract 3? Those are 7 times 4. My plus goes to the larger number, x plus 7 and x minus 4. Now, if you look at this, my x minus 4s will then cancel. So this is the same thing as finding the limit as x approaches 4 of x plus 7. Those are identical because these are equivalent expressions, right? Even though I canceled these out, this is equivalent. And now all I have to do is take the 4, plug it in, and you get the limit to be equal to 11. Final answer. Last example of the day, a little bit more factoring. Let's do the limit as x approaches 3 of x to the third minus 3x squared plus x minus 3, all over x to the fourth minus 3x cubed minus 2x plus 6. Now let's check just to be sure, because I have a feeling that I'm going to get 0 in the bottom. If I take 0 and plug it into the bottom, that gives me 3 to the fourth power, which is 3 times 3 times 3 times 3, which I think is 81, minus 3 to the third power times another 3 is really just 81 again, minus 2 times 3 is 6 plus 6. This is all canceled out. So yeah, I am going to get 0 in the bottom, which means this is not going to be a way to go. So I got to figure out a way to maybe factor this thing and see if we can get some stuff to cancel out and make it easier. When we have 4 terms, we are going to use something called grouping. I am going to put a line down the middle and divide my 4 terms into 2 groups. And I'm going to factor them that way. Look at the first group only. The greatest common factor is x squared. So I'm going to take an x squared out in the front like this. Take an x squared out of x to the third, and you're left with x. Take an x squared out of negative 3x squared, and you're left with negative 3. In my second group, I really have nothing here that's the greatest common factor. So let's put this as a 1, and my x minus 3 comes over by itself. When the 2 groups that you have left on the inside of the parentheses match, that is good because we can then factor those 2 groups. Let's do the same thing to the bottom. I'm going to divide this into 2 groups. Take that minus with the 2x over here in the second group. My first group, x to the fourth minus 3x to the third, has an x to the third as a greatest common factor. X to the fourth divided by x to the third is just x, and negative 3x to the third divided by x to the third is minus 3. That's good news. My second group with the minus. Now kind of look, I want to have this group match, and I want to have an x come out here. And in my first term is a negative 2x. Let's factor out a negative 2 and see if that helps. I take a negative 2 out of negative 2x, gives me x. And if I take a negative 2 out of a plus 6, that would give me a minus 3, because negative 2 times negative 3 is a positive 6. Now, my grouping says, in my first group I have an x minus 3. In my second group I have an x minus 3. So that factors as x minus 3 times something. Well, if I take the x minus 3 out, what's left? An x squared plus 1, so that's my other factor. Once again, for my other terms down here, I can take out an x minus 3, and when I factor an x minus 3 out of there, what's left? X to the third minus 2. Now my 2 x minus 3s will cancel, which makes some sense because when I took the 3 and plugged it in, that gave me 0 on the bottom, so that's a no-go. So I'm now evaluating the same function of the limit as x approaches 3, but instead now I'm using x squared plus 1 over x cubed minus 2. And so what are we going to do with this? Well, this is the same as the quotient property. I can now just take these and evaluate these as 2 individual polynomials by taking the limit from both sides, the positive and the negative, and plugging them in. In the top, I have 3 squared, which is 9 plus 1, which is 10. And on the bottom, I have 3 to the third power, which is 3 times 3 times 3, which is 27. And 27 minus 2 is 25. And this now reduces to 2/5. And that is my final answer. I hope that has been helpful for you. This is a very Very important technique in order for you to understand calculus and the derivative. So if you have any other questions, please email me or contact me on Remind or find me in room 312. Have a great day.